Oh my god. All right. Okay. Well. Okay. So sorry, I just missed out on what was that? 15 minutes? Yeah. All right. 15 minutes of footage has been lost to time. This is great. We're doing good. Wish you were here. See my face, but it's good. All right. Okay. Quick recap of where I was here. All right. All right, plot for today. Numerical sets. All right, we're talking about last time, complex numbers, but first I want to do a little recursion stuff. Here is recursion for sigma notation, for products, and here's the recursion for exponents. This is what we're currently discussing, and we're in the middle of a proof of recursion with exponents, proving a fact about exponentiation that you knew before you started watching this embarrassing video. All right, so get us up to speed here. All right, so we noted that there are two positive integers here, non-negative integers, but if you do want to induct, you don't need to induct on both. You can just be, well, this one will keep locked down, and then we'll induct on m. And because we picked n arbitrarily, if you just induct on m, then it works for all n as well. All right, so there we go. So we took care of the base case, and again, following our definition of how exponents should work. That's how it went down. So we did n plus 0. We know adding 0 doesn't do anything. We know multiplying by 1 doesn't do anything. And 1 is equal to x to the 0. All right, so now that took care of the base case. And again, with the induction, I don't care if you formally write out base case and induction hypothesis. As long as somebody knows you're doing induction, they can read it and understand it. Like in mathematical papers and published research, nobody goes base case, induction. Nobody writes that shit. All right. Okay. All right, so now we are assuming this. And note here, again, like I did last time, I'm using a different m just for, emphasis, right? You can use lowercase m here, but I think for, clarity, a capital M kind of gives you an idea of, well, it's not all m. I'm picking a specific m and showing things work. So, all right. All right. Now, what am I going to do? Well, note, I'm assuming that, so I want to use it, but I also want to use my exponent rules to help me out here. And where do I want to start now? Well, note that I'm doing an induction proof, so I need to now look at m plus 1. Right? I showed it works if m is 0. I'm now supposing it works for m, and then showing that it works for m plus 1. So if I know it works for 0, and I know I can iterate, that means I know it works for 0, then I know it works for 1, I know it works for 2, so on and so forth. All right, so how am I going to use it here? Well, let's think about what I've got. Well, as I said, kind of an unsung hero of the additive axioms is our good friend associativity. Meaning that I can move my parenthesis over without issue. All right, and then now what can I do here? Well, by the definition of exponentials by recursion, hey, if I got a plus 1, I know it splits like that. So that splits like that. But now I have an n plus m, and I know by induction that breaks apart. By the induction hypothesis, I know that breaks apart the way I want it to. Hey, so note here I've got 3 things multiplying up. I don't need to worry about parentheses because multiplication is associative. I was being a real stickler about it. I could do that, but we can move on with our life. And then now what am I going to do? Well, now I see, hey, I know what this is equal to because equality goes both ways. It lets me turn this into that, but it also lets me turn this into that. So this lets me turn that into that, and there we go. We have now proven that, hey, if I have x to the n plus m, it splits like that. And from that, I can prove that if I have x to the n plus quantity m plus 1, that also splits the way you want it to. There we go. I proved that if you know it's good for m, it also works for m plus 1. And since I established a base case, I then know it's going to work for all of the integers starting from 0 and beyond. All right, another nice little induction proof. Good stuff. All right, and again, I wanted to go through that because there are exponent rules that you know are true, but now I've got a proof. And it's worth noting that you can then go ahead and prove your other exponent rules that you might be familiar with. X to a product is x to the n to the m. And there are other ones you can prove that one by induction now, too, if you really wanted to. All right. Now, why I really wanted to do this is because I wanted to make it clear that when you square something, that works the way you think it should. When we think of x squared, we know that it means multiply by itself. And if we follow the rules here, well, 2 is 1 plus 1. Which, note, you don't need to prove. That's the definition of 2. I know it's like there's like the meme that like it took mathematicians hundreds of pages to prove it. Well, sort of. That was Principia Mathematica by Russell and Whitehead, and they were doing all sorts of wacky shit there, and like they needed to prove it. That's dumb. 2 plus 2 is 1. What? 1 plus 1 is 2. The other. What did I say out loud and recorded? Right. The thing you really need to prove is 2 plus 2 is 4. You actually need to prove that. But 2 is 1 plus 1. All right. But if we're following the definition, then that would split into x to the 1 times x. And x to the 1, well, right, you can then follow the same logic and get that, missing a step there. That's really x to the 0 plus 1 x. Which would then be x to the 0 x, or if I'm really going to be careful about it. All right, there we go. All right, type it all up. All right, got a double seat up. Yeah. All right, so yeah, there is, in all of its gory detail, actually computing out that x squared is indeed what it's supposed to be. Right, following the recursive, right, because I know what happens at 0. If I want to figure out what happens at 2, well, then I bring it down to 1, and then I bring 1 down to 0, and I know what happens at 0, and then you upscale. Cool. All right, but squaring, indeed, following the recursive definition, does what we think it should do. It's itself multiplied by 2. You can verify that for 3 and beyond. If you really want to convince yourself that x to the 5th is really what it's supposed to be, you can. All right, now squaring is a very powerful and common tool in mathematics. And there's something you can prove about squaring and ordering of real numbers. And that is that squaring a real number must always result in something greater than or equal to 0. 0 squares to 0, because it's 0 times 0, but any other real number, if you multiply by it, well, one of the rules for multiplication and ordering is that multiplying two positive things remains positive. And 1 you can prove has to be positive from the other ordering rules of the real numbers, so from there you're good to go. All right, so this has to be true. However, there's a bit of a problem. With this. If you add 1 to both sides of that inequality, you then get that x squared plus 1 is always bigger than 0, so it's never actually equal to 0. Right? It's always greater or equal to 1, in fact. In fact, you can use calculus and prove that 1's the minimum. However, expressions like x squared plus 1 equals 0 do show up in mathematics, and they need an answer. And historically, the reason this came about was in the 1500s, Italian mathematicians were trying to get the roots of cubic polynomials. The quadratic equation was known They knew how to get roots of quadratics, and they knew quadratics sometimes don't have answers. But when they went over to the cubics and tried solving those, they found a formula, particularly a guy named Cardano found a formula, and then he noticed something weird about his formula. If he pretended that there was something that squared to -1, he could plug that into his formula and then get real answers. So if he pretended you could do that, you actually could get solutions. So he was like, all right, this is a thing. There's something that squares to -1, and we're allowed to use it. And good old Rene Descartes, as he does, butted in and went, these guys with their imaginary numbers. So, the name sort of stuck for the years, but as they became more obvious that they were incredibly useful in many facets of mathematics, they're now called complex numbers, with the origin of the name imaginary and the symbol we use for the fundamental thing. Historically, that's where it came from. It goes back to good old Descartes, who already thought negative numbers were a load of bullshit, and that animals don't have souls, so, you know. But, hey, the Cartesian plane was a good idea. He wasn't completely wrong about stuff. I think, I doubt, therefore I think, therefore I am. Pretty good. You know, not a bad idea, I guess. All right. So, expressions like x squared plus 1 have to have an answer, and because if they do, then every polynomial can be factored, and that leads us to introduce the set of complex numbers. All right, and so what is this set exactly? All right, so the set of complex numbers, following our little discussion here, I need something that squares to -1 to cancel 1 to get 0. All right, so the set C of complex numbers is the collection of all things that look like A plus BI, where A and B are real numbers, and I squares to -1. Right, note how I wrote that. I did not write square root of -1 is I. Not true. It's a half-truth. One of the answers to the square root of -1 is I. The other one is -I. If you want to get really precise, the principal root of -1 is I. If you are taking Math 365, then you already know this, or eventually you'll learn it. And if not, take Math 365 next spring. Okay, so it's much better to think of I as squaring to -1, rather than I is the root of -1. That leads to some bad math, because square root, we believe, has like multiplicative properties. Square root of A times B is the square root of A times the square root of B. That's good for positive real numbers. It falls apart for the negatives, unfortunately. And it has to deal with complex square roots just don't behave in a meaningful manner. All right, cool. All right, so that's the story. That's all they are. Right, but there are a lot of ins and outs and what have yous that we should discuss here. So the first thing we're going to prove is that if you give me a complex number, it looks like A plus BI. Are A and B unique? Right, the immediate intuition, yeah, of course, obviously. Right, but that's not my definition. My definition is, yeah, you look like A plus BI. I didn't say you have to be a precise A and a precise B. There is an A and there is a B, and there is this thing I that works. All right, so let's actually prove that A and B are unique. And so, formally then, that would mean that I'm proving that if A plus BI is equal to C plus DI, then A has to equal C, and B has to equal D. And then this lets us look at this complex number and go that, well, all right, well, A is the real part, and B is the imaginary part. And this will have some notation that we'll see in a moment. But let's actually explicitly prove this. And the key step to the proof is to group your like terms together. Subtract C over and subtract BI over, you'll get this. Now, we'll go for a contradiction. I want B to equal D. Well, suppose it doesn't. Then B minus D is non-zero, and then I can divide it over. And now what happens? Well, now square both sides. And if I square both sides, well, on the right, I'll have a real number squared, which we know is bigger than 0. But then on the right, when we're squared, hey, look at that, you'll have -1. So I've got -1 is bigger than 0, which I think we all agree is not correct. So I have derived a contradiction. So that means that B minus D actually has to equal 0. And that means that B has to equal D. And going back to this equation there, that means that 0 is out, which gives me A minus C is 0. So then A has to equal C. So there we go. Following the rules of how multiplication and addition should work, we can prove directly that, yeah, A plus B, that's unique. All right, cool. So there we go. Nice little proof. All right. So because of that, then, we can make the following definition. So given a complex number z, we can then define its real and imaginary pieces, which are written as follows: real z, im z. So it's worth noting this is the modern notation. If you go back far enough, you'll find mathematicians that will write that. Ugh, disgusting. And actually, there are some modern people that still use this. This is an old notation. But it's out there. But it's built into LaTeX. If you do /re and /im, that's what you get. So you have to come up with your own commands for the more modern, real and imaginary part. Right. And what are they again? They are the unique A and B out of the reals, so that z is actually equal to A plus BI. Cool. We proved there's unique ones, so we can give them fancy symbols because they're unique. Yeah.
Do we know that the axioms for the rational numbers also hold for complex numbers? Because you use the fact that 0 multiplied I is equal to 0. Up there in order to. Once B minus D is equal to 0, so 0.
0 times. Yeah. So okay. So the additive and multiplicative axioms that I was talking about for the reals, they hold for C as well. So if I was being really proper about this, I'd be here's exactly what I would say. I would say C is a field, so it has additive and multiplicative, and it works the way you want it to. That contains the real numbers and has the property that every element looks like A plus BI, where A and B are real numbers, and I behaves the way you want it to. So, yes. So the additive and multiplicative rules for the reals still apply for the complex numbers. So, all right. So now that we've got the real and imaginary notation, there are some things you can prove. So, for example, if I've got a complex number z and a complex number w, well, it's a plus bi and c plus di, and the rules for addition and multiplication still carry over with this I symbol. And here we see that, hey, z plus w is a plus c plus a plus d quantity times I. And from that, you can then get some neat little formulas for your real part and imaginary part. In particular, this tells me that real part and imaginary part are something called additive mappings, meaning that if you feed it a sum, you get the sum of the outputs. It's our favorite phrase in mathematics. The x of the y is the y of the x. The real part of the sum is the sum of the real parts. Right? So much math is devoted to whether or not that statement is true. Right? Sum of the derivatives is the derivative of the sum. Right? Integral of the sum is the sum of the integrals. So much math is like, all right, is the x of the y of the x? If it is, great. If it's not, why? Cool. All right. Now, it's worth noting there are other fun little formulas out there with the real and imaginary parts. You can look at the real and imaginary part of a product. Formulas get a little gross, but they're out there. Maybe on a problem list. All right. All right. And won't get too sweaty about that. I want to talk about two more complex ideas, and we'll call it a day. So, a very powerful tool when it comes to complex numbers is a very interesting one. And it's something called the conjugate of a complex number. So note, every complex number is its real part plus its imaginary part times I. Its conjugate is replace the plus with a minus. It's a weird thing to think about, like, oh, okay. Like, so for example, was it yelling at me about, I'm getting a undefined control sequence. I don't know what the fuck you're talking about. All right, there's a Z right there. All right, so for example here, if I conjugate 1 minus 3i, you get 1 plus 3i. Right, it changes the plus to a minus, and vice versa. Right, because note here, there is no subtraction. Again, it's adding by negatives. So that's really 1 plus quantity negative 3i. And then you'd have the minus, and the minuses will knock out. All right, now geometrically complex numbers can be thought of as points in the plane, and note that this would correspond to reflecting across the x-axis. So there's a geometry here that you can, if you keep it in your mind, you can exploit and come up with some nice intuition. We're not going to get too crazy about that, but it's worth noting that it's out there. And we don't have time, but I will note that you can prove the following. The conjugate of a sum is the sum of the conjugates, and the conjugate of the product is the product of the conjugates. So, if you want a nice little challenge after class today, go ahead and try to prove these. But not too bad. One of them is immediate from this little brief argument we made right here. Right, because note here, this would be the sum, and so the real and imaginary parts behave the way you want them to. The product's a little more challenging. It requires a little more work, but you can do it. Also, something that you can prove is the following. If you take z and multiply it by its conjugate, note that you'd have real part plus imaginary part times I, multiplying real part minus I minus imaginary part times I. So you'll pick up the real part squared, you'll pick up the imaginary part squared, but no complex terms will show up. Hey. Oh man, this is pretty interesting. I've got a sum of two squares. And if we think about complex numbers hanging out in the plane, oh, this kind of looks like a base and a height of a right triangle. Like the Pythagorean theorem or something. Oh boy. All right, so we should probably introduce, and this is the last thing we'll talk about today, the modulus of a complex number. Which is that right there. You take the square root. Right, so as I mentioned, you kind of think of complex number hanging out in the plane, right? It's got a real part, an x-coordinate, imaginary part, a y-coordinate, and you can make a triangle. And then you can get the distance from the origin, which would be precisely that square root. All right, so modulus of a complex number works very much like how absolute value works, and in fact, for a real number, this is equal to the absolute value, hence why we use the same symbol. And there are many things about modulus that are true. I'll give you a quick list of facts here. And we're not going to have the time to prove it today, and I want to move on to other topics, but it's worth knowing the following things can be proven to be true. And that'll finish us off for today. All right, so first of all, note that we can recontextualize this fact using the definition. Z times its conjugate is the modulus squared. And this then gives you a formula of finding the reciprocal of any complex number. So 1 over z can be computed now, because if z is, bring the 1 over z over. If z is not equal to 0, well then it's not the origin, so its modulus is non-zero, and you can divide that over. And hey, if you want to get your reciprocal, here's a quick formula for it. Compute the conjugate, compute the modulus, take the quotient. Good stuff. Something we know about absolute values of real numbers is that they're multiplicative. And again, our favorite phrase, the x to the y is the y to the x. The modulus of a product is the product of the moduli. So you can directly prove this one, it's not too hard. One that requires a little bit of effort and trickery is the following, and this is the last thing I'll note for today. Something that you may or may not know modulus, absolute value does, is that if you take the absolute value of a sum, it doesn't equal the sum of the absolute values, but it never gets bigger than that. That's the same thing is true for complex numbers. The modulus of sum is less than or equal to the sum of the modulus. So if we can't get the x to the y is the y of the x, then maybe we can get the x of the y is less than the y of the x or something like that. That happens here. This is called the triangle inequality, and you can intuitively convince yourself this is true by just picking 2 points in the plane z and w, think where z plus w is, and then measure the lengths. And you'll say, yeah, obviously. But proving this actually is pretty non-trivial. It requires some tricks. And I'll give you the idea, and I'll leave class with that. The idea of the proof is, instead of starting with modulus of z plus w, start with the modulus squared. And why would you want to do that? Well, note, modulus squared, oh hey, there's something else it's equal to that I can algebraically work with, and that ends up being kind of the trick. Good stuff. All right, and with that, that's about all the stuff I want to talk about with complex numbers. Again, we'll get a little more practice with them as the semester goes. They're going to show up when we factor polynomials, so when we get there, we'll do it. But that's it for today. Oh, yeah, where's... I just didn't even write it. I said it, and I didn't write it. Yeah, no, good stuff. All right, thanks for the correction. All right, cool. All right, that was it for today. We'll see you on Monday. With hopefully no disruptions.